The eternal question: what shape is our universe? Humans have always looked up at the night sky with wonder. We have pondered our place in the vast cosmos. One of the most profound questions we ask is about the universe itself. What is its overall shape? Is it infinite, stretching out forever in all directions? Or does it have a boundary, an edge we might someday reach? Today our tools are far more advanced. We use powerful telescopes and complex mathematics. Yet, the fundamental question about the universe's geometry remains a frontier of scientific exploration. It drives us to peer deeper into space and time. The shape of the universe is not just an abstract geometric puzzle. It is deeply connected to its origin, its evolution, and its ultimate fate. Understanding this shape could unlock secrets about the Big Bang. It could tell us if the universe will expand forever or perhaps one day collapse back on itself. Imagine trying to understand Earth without knowing it is a sphere. Early sailors feared falling off the edge. Knowing Earth's true shape revolutionized navigation and our understanding of our world. Similarly, knowing the universe's shape would revolutionize our understanding of everything. This journey into cosmic geometry is filled with mind-bending ideas. We encounter concepts that challenge our everyday intuition. Scientists use analogies to help us grasp these possibilities. Join us as we explore these mind-blowing cosmic theories. Cosmic geometry: flat, open, or closed like a sphere. When cosmologists talk about the shape of the universe, they usually refer to its overall geometry. There are three main possibilities based on Einstein's theory of general relativity. These are often described as flat, open, or closed. A flat universe is the simplest to imagine. It's like an infinite flat sheet of paper. Parallel lines in a flat universe remain parallel forever. The angles of a large triangle would add up to exactly 180 degrees. The second possibility is an open universe. This type of universe has a negative curvature. Imagine the surface of a saddle or a Pringle chip. Parallel lines in an open universe would eventually diverge, moving further apart from each other. The third possibility, and the focus of our discussion, is a closed universe. This type of universe has a positive curvature, like the surface of a sphere. In a closed, spherical universe, parallel lines would eventually converge and meet. If you could draw a gigantic triangle, its angles would add up to more than 180 degrees. Crucially, a spherical universe is finite in volume. However, it has no edge or boundary. Understanding these geometries is key to understanding modern cosmology. A historical gaze: early attempts to map the cosmos. The quest to understand the universe's shape is as old as human consciousness. Ancient cultures developed intricate myths and models. The Babylonians meticulously charted the stars for divination and calendrical purposes. The ancient Greeks were among the first to apply geometry to the cosmos. Thinkers like Pythagoras and Plato imagined a harmonious universe governed by mathematical principles. Aristotle proposed a geocentric model, with Earth at the center, surrounded by concentric crystalline spheres carrying the planets and stars. This model, later refined by Ptolemy, dominated Western thought for over a millennium. The Renaissance brought a revolution in cosmic understanding. Nicholas Copernicus proposed a heliocentric model, placing the sun at the center. This was a monumental shift. Einstein's canvas: general relativity and cosmic curvature. Albert Einstein's theory of general relativity is the cornerstone of modern cosmology. It provides the mathematical framework for understanding the universe's shape. Before Einstein, space was considered a passive, unchanging stage. Newton's laws played out in this fixed arena. General relativity, however, revealed that space and time are interwoven into a single entity: space-time. This space-time is not passive, it is dynamic. It can bend, warp, and ripple in response to the presence of matter and energy. Think of a bowling ball placed on a stretched rubber sheet. The bowling ball creates a dip, a curvature in the sheet. This curvature of space-time is what we perceive as gravity. Planets orbit stars not because of a mysterious force pulling them, but because they are following the curves in space-time created by the star's mass. Einstein's field equations, the heart of general relativity, relate the geometry of space-time to the distribution of matter and energy within it. Section 5. The spherical proposition: a universe finite yet unbounded. The idea of a spherical universe is perhaps the most intriguing of the three main geometric possibilities. A spherical universe is described as having positive curvature. This means that on the largest scales, space itself curves back on itself, much like the surface of a sphere. One of the most mind-bending aspects of a spherical universe is that it is finite in volume. It contains a limited amount of space. Yet, remarkably, it has no edge or boundary. This concept challenges our everyday intuition, which is shaped by living in what appears to be a three-dimensional Euclidean space with no obvious limits. To grasp this, let's return to the analogy of an ant on a balloon. The balloon's surface is two-dimensional. For the ant, this surface is its entire universe. The ant can walk in any direction. It will never encounter an edge or fall off. If the ant walks in a straight line for long enough, it will eventually circumnavigate the balloon and return to its starting point. Section 6 Echoes of the Big Bang. Introducing the cosmic microwave background. One of the most powerful tools scientists use to study the universe's shape is the cosmic microwave background, or CMB. The CMB is often described as the afterglow of the Big Bang. It is a faint, pervasive radiation that fills all of space. Its discovery in 1964 by Arno Penzias and Robert Wilson was a landmark moment in cosmology. They were trying to use a new horn antenna for Bell Labs but detected a persistent, unexplained noise. This noise turned out to be the oldest light in the universe, a relic from a time when the cosmos was incredibly hot and dense. This discovery provided strong evidence for the Big Bang theory. The early universe, for the first few 100,000 years after the Big Bang, was a very different place. It was a seething, opaque plasma of fundamental particles and radiation, primarily photons, electrons, and protons. Photons were constantly scattering off free electrons, much like light scatters in a dense fog. This meant that light could not travel very far. The universe was opaque. As the universe expanded, it also cooled. Eventually, after about 380,000 years, it cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This event is called recombination or decoupling. Section 7. Decoding the CMB. How ancient light reveals cosmic shape. The tiny temperature fluctuations in the cosmic microwave background are not random. They form a specific pattern across the sky. This pattern contains a wealth of information, including vital clues about the overall geometry of the universe. Scientists analyzed the characteristic size of the hot and cold spots in the CMB. The apparent angular size of these spots, as we observe them today, depends on the path the light from these spots has taken to reach us over billions of years. This path, in turn, is dictated by the curvature of space. It's like looking at an object through different kinds of lenses. Imagine a spot of a known physical size in the early universe. If the universe is flat, light from that spot travels in straight lines. We would observe its angular size as expected by standard Euclidean geometry. Is our universe truly a sphere? The Planck satellite suggests the universe is nearly flat. If spherical, it must be vast with undetectable curvature. Imagine an ant on a colossal balloon. To the ant, it appears flat. Our universe might be a similar patch. Inflation theory predicts a flat universe. Some data hints at slight positive curvature. Section 9. Why Shape Matters. The Ultimate Fate and Our Cosmic Address. Understanding the shape of the universe is not merely an academic exercise in cosmic cartography. It has profound implications for our understanding of fundamental physics, the origin of the cosmos, and its ultimate destiny. The geometry of the universe is intimately linked to its total energy density, as described by Einstein's equations. If the universe is indeed spherical, it implies that its average density is greater than the critical density. This, in turn, would have significant consequences for how the universe will evolve in the far future. A closed, spherical universe is typically associated with an eventual halt to its expansion and a subsequent recollapse. This scenario, often dubbed the Big Crunch, paints a dramatic picture of the universe's end. After billions of years of expansion, gravity would eventually win out, pulling all matter and energy back together. Galaxies would rush towards each other, merging and colliding. The universe would become hotter and denser, eventually collapsing into an incredibly energetic singularity, perhaps mirroring the conditions of the Big Bang. While current observations of accelerating expansion make an imminent Big Crunch unlikely, the fundamental geometry still holds clues. If the universe is truly spherical, the interplay between its matter-energy content and dark energy will dictate its long-term fate. Furthermore, The shape of the universe can provide tests for fundamental theories, including theories of quantum gravity and string theory.